For the first time in history, humanity has discovered something more terrifying than an infinite universe. It's a universe that is expanding so fast that, every second, more of it slips beyond our reach forever, even if we could travel at the speed of light. In this video, you'll uncover why the fastest speed in existence still loses to the universe itself, and what that reveals about humanity's future among the stars. Get ready. Let's begin. Are you absolutely sure that the speed of light is the fastest thing you will ever need? Most people would say yes without hesitation. The speed of light sits at the top of every science textbook, every documentary, every conversation about the cosmos. It is the trophy humanity holds up when we talk about what the universe allows. It is the dream we reach for when we imagine someday leaving this planet behind and actually going somewhere. And for most of human history, that assumption felt reasonable. If we could only move that fast, if we could only crack that one final barrier, then the stars would open themselves up to us. The cosmos would surrender. That assumption is the most fundamental mistake you can make about the universe. Here is what light speed actually is: 299,792 kilometers per second. Not a round number chosen for convenience. Not an engineering target someone arbitrarily set. This is the speed at which causal information propagates through the fabric of reality itself. Every signal, every influence, every ripple of cause reaching out toward effect, all of it travels at exactly this speed and no faster. This is not a technological ceiling waiting to be shattered by a more powerful engine or a more clever fuel. It is a logical boundary. It is the speed at which the universe processes the relationship between one event and the next, which means it cannot be broken. Not eventually. Not with better tools. Not ever. Ask yourself why, and the answer is not complicated, but it is devastating. If something could travel faster than light, it would, in certain reference frames, arrive before it departed. The effect would precede the cause. A bullet would reach its target before the trigger was pulled. A message would be received before it was sent. The entire ordered sequence of events that makes reality coherent, that makes cause come before consequence, that makes time flow in a single direction, that makes the story of the universe tell itself in a sensible order. All of it would dissolve. The universe is not being cruel by enforcing this limit. It is being consistent. Without this speed ceiling, reality as a structured, meaningful thing simply could not exist. So the speed of light is not a reward the universe offers to civilizations advanced enough to reach it. It is the ceiling the universe installed to keep everything, every particle, every signal, every ship that will ever be built, locked inside the only kind of existence that makes logical sense. And now consider what it took for humanity to even discover this ceiling existed. For most of recorded history, people assumed light was instantaneous. You open a shutter, and the room floods with brightness in the same moment. There seemed to be no delay, no travel time, nothing to measure. Then, in 1676, a Danish astronomer named Ole Rømer was doing something far more mundane than searching for the speed of light. He was tracking the orbital schedule of Io, one of Jupiter's large moons, watching it disappear and reappear from behind the giant planet with mechanical regularity. And he noticed something that did not fit. When Earth sat on the near side of its orbit relative to Jupiter, Io's reappearances came slightly earlier than predicted. When Earth swung to the far side of its orbit, those same reappearances arrived slightly late. Rømer recognized what this meant. The light carrying the image of Io's emergence had a longer distance to travel when Earth was farther away. That delay was not an error in his calculations about the moon's orbit. It was the travel time of light itself, stretched across the extra distance between the two planets. From a small discrepancy in a moon's schedule, humanity pulled out something extraordinary proof that light has a finite speed. It takes time to get from one place to another. The universe was not updating itself instantaneously. Every piece of information traveling across space was paying a price measured in time for every inch of the journey. That single insight changed everything. It meant that looking outward into space was identical to looking backward into time. The moment you observe anything beyond your immediate surroundings, you are seeing it not as it is, but as it was as far back in time as it took light to reach your eye. Light takes time, and that time, that unavoidable, irreducible, non-negotiable cost built into the very structure of the universe, is where tonight's story gets terrifying. But before we talk about distance, we need to talk about what the speed of light actually does to your time when you reach it. The answer will make you not want to go there anymore. If you came home still young, still sharp, still carrying the same face you left with, but everyone you had ever loved was gone, buried, turned to memory, would you call that a victory? Take a moment with that question, because it is not a hypothetical designed to make you feel something. It is a precise description of what the universe has actually built into the architecture of high-speed travel. And understanding it changes everything about what it would mean to reach the stars. When Albert Einstein published his special theory of relativity in 1905, one of its most disorienting consequences was this time does not pass at the same rate for everyone. The faster you move through space, the slower time moves for you relative to someone standing still. This is not a trick of perception. It is not an optical illusion or a philosophical abstraction. It is a measurable, repeatable, confirmed physical fact, and we have the data to prove it. In 1971, physicists Joseph Haffel and Richard Keating placed extremely precise atomic clocks aboard commercial aircraft and flew them around the world. When those clocks landed and were compared against identical clocks that had remained stationary on the ground, the airborne clocks showed slightly less elapsed time. The difference was tiny. We are talking about fractions of a microsecond, but it was exactly what Einstein's equations predicted. Time had genuinely passed more slowly for the clocks in motion. Nature has been running this experiment for far longer than we have, and on a far more dramatic scale. Every second, cosmic rays streaming in from deep space slam into the upper atmosphere of Earth and produce particles called muons. A muon is unstable. Its theoretical lifespan is approximately 2.2 microseconds, far too short, by any standard calculation, for it to survive the journey from the upper atmosphere down to the ground. The distance is simply too great. At the speed muons travel, they should decay and vanish long before reaching sea level. And yet they arrive. Detectors at the surface register them constantly. The reason is time dilation. Muons travel at roughly 98% of the speed of light, and at that velocity, time slows so dramatically for them that what feels like 2.2 microseconds from their own frame of reference stretches into enough time from our perspective to complete the journey. These particles are not defying physics. They are obeying it perfectly. And they are proof, written in real data, that time is not fixed. Now take that principle and apply it to what a near light-speed journey would actually mean for a human being. In 2015, NASA confirmed Kepler 452b as one of the most Earth-like exoplanets ever identified, a rocky world orbiting a sun-like star in the habitable zone, sitting 1,400 light-years away from us. Imagine boarding a ship capable of traveling at 99.9999% of the speed of light and setting a course for that planet. From the perspective of everyone you left behind on Earth, the journey takes 1,400 years. 1,400 years of human history unfold while your ship cuts through the dark. But inside the ship, due to the extreme time dilation at that velocity, you experience only a few decades. You arrive at another world, still alive, still relatively young, carrying memories of a home that has not existed for over a millennium. You are not traveling through space. You're traveling out of your own era. Every person you knew when you left has been dead for centuries. The language you spoke may have shifted beyond recognition. The way Latin quietly transformed into something unrecoverable. The country where you were born, its borders, its institutions, its name may belong entirely to the history books. The world that shaped you, that gave you context and meaning and belonging, has been replaced so many times over that nothing recognizable remains. You did not skip across the stars. You were erased from your own time. This is the twin paradox, and it is one of the most famous illustrations of what special relativity actually means in human terms. One twin stays on Earth, the other boards a ship and travels at near light speed to a distant star before returning. When they meet again, they are genuinely different ages. The traveling twin is younger, not because of any medical intervention, not because of any trick, but because time physically passed more slowly for them. The universe aged the two siblings at different rates. And when they stand in the same room again, the gap between them is real, irreversible, and absolute. This is not a metaphor. It is what space-time does when you push against the speed ceiling hard enough. And so the dream quietly reveals its true face. The speed of light does not offer you immortality. It does not give you the universe. It gives you the most perfect loneliness. The cosmos knows how to manufacture the loneliness of arriving somewhere vast and strange, young and breathing, in a time that belongs to no one you have ever known. But now suppose you accept that trade. Suppose you are willing to leave everything behind. Where does the first journey actually take you, and how long does it take to get there? The number that is coming will change the way you look at the darkness outside your window. If there is a planet that might harbor life sitting just 4 light years away from us, why do we still know almost nothing about it? That question is not rhetorical. It carries inside it everything that is both thrilling and crushing about our position in the cosmos. 4 light years sounds, on the surface, like a manageable number. You have heard larger figures thrown around in casual conversation. 4 of anything seems approachable. And yet that number, that deceptively small-sounding number, represents a gulf so vast that no human technology ever built has come remotely close to crossing it. And it is, without qualification, the shortest interstellar distance we will ever discuss tonight. The nearest star system to our own is called Alpha Centauri. It is not a single star, but a family of 3. Alpha Centauri A and Alpha Centauri B are a paired set of stars orbiting each other in a slow gravitational waltz, both of them broadly similar to our own sun in size, temperature, and composition. Circling the outer edges of that pair, at a distance so large it may take hundreds of thousands of years to complete one orbit, is a third member, Proxima Centauri, a small, dim red dwarf star. And right now, Proxima Centauri holds the title of the closest star to Earth at 4.24 light-years away. Every other star in the observable universe is farther. In 2016, the European Southern Observatory confirmed something extraordinary about Proxima Centauri. It has a planet, designated Proxima Centauri b. This world sits within its star's habitable zone, the orbital range where temperatures could theoretically allow liquid water to exist on a surface. Its minimum mass is estimated at 1.07 times the mass of Earth. Rocky, potentially Earth-sized, orbiting the nearest star. For anyone who has ever looked up at the night sky and wondered whether we are alone, the discovery of Proxima Centauri b felt like the universe leaning closer and whispering something, but the universe almost immediately took that whisper back. Proxima Centauri is not a gentle star. Red dwarfs of its type are among the most violently unpredictable stellar objects known to science. Unlike our relatively stable sun, Proxima erupts with enormous flares that blast ultraviolet radiation and X-rays into surrounding space at intensities hundreds of times greater than anything Earth typically receives from its own star. In 2017, astronomers recorded a single flare from Proxima Centauri so powerful that, had Proxima Centauri b possessed any meaningful atmosphere at the time, that one event alone carried enough energy to strip it away entirely. One flare, one bad day for a star and a planet's entire atmospheric protection. Gone. Whether Proxima Centauri b has managed to retain an atmosphere, whether it has a magnetic field strong enough to deflect that constant bombardment, whether liquid water could survive on its surface despite the radiation environment, none of these questions have been answered. We do not have instruments capable of answering them from here, and getting instruments there is a problem that illuminates exactly how merciless these distances truly are. In 2016, physicist Stephen Hawking and entrepreneur Yuri Milner publicly announced Breakthrough Starshot, one of the most audacious space proposals in the history of science. The concept was to build miniature spacecraft, each weighing only a few grams, and accelerate them using powerful ground-based lasers to 20% of the speed of light. At that velocity, the journey to Proxima Centauri would take approximately 20 years of flight time. Add 4 years for any signal the craft sends back to reach Earth, and you are looking at a minimum of 24 years before humanity receives its first close-up data from another star system. The project remains in research and development. No such craft has been launched. The engineering challenges involved protecting a gram-scale chip from interstellar dust particles at relativistic speeds. Steering it, powering its transmitter are formidable enough that no timeline for an actual mission currently exists. And that is our most optimistic real-world plan for reaching the nearest star. A gram-scale chip. 2 decades of flight? No human aboard. Now consider what our actual farthest-reaching spacecraft has accomplished. Voyager 1, launched in 1977, has been traveling continuously for nearly half a century. As of 2024, it sits approximately 23 billion kilometers from Earth, farther than any human-made object in history. That sounds extraordinary. It is extraordinary. And the distance to Proxima Centauri is 40 trillion kilometers. Voyager 1, traveling at its current speed on a direct course toward that star, which it is not doing, would need approximately 73,000 years to arrive. 73,000 years. That is longer than modern Homo sapiens have existed in their current anatomical form. The nearest star is not near. It is an abyss wearing a small number as a disguise, and this is the part that deserves a moment of stillness. 4.24 light-years is the minimum. It is the closest possible first step. Every other destination in the universe, every other star, every nebula, every galaxy is farther. Some are thousands of times farther. Some are billions of times farther. The nearest star to our own represents the bottom rung of a ladder whose top cannot be seen, cannot be imagined, and cannot be reached. All right, 4 light-years for the nearest star. Now multiply that number not by 10, not by 100, by tens of thousands. Because what we are about to talk about is not a single star. It is our entire galaxy. If the Milky Way were a city vast, sprawling, lit from within by hundreds of billions of points of light, where exactly would you be living in it? Not downtown, not anywhere near the gleaming center with its dense towers of stars packed so tightly that the night sky would blaze bright enough to read by. Not on the outer edge either, in the thinning suburbs where stars grow sparse and the darkness between them stretches longer. You would be somewhere in between in a quiet, unremarkable stretch of one of the city's smaller side streets, far from the grand boulevards, far from the dramatic core, tucked into a modest spur between 2 of the galaxy's larger structures. You would be, in the most precise sense of the word, in the cosmic equivalent of a peaceful neighborhood that almost no one specifically talks about. That is exactly where we are. The Milky Way spans approximately 100,000 light-years from one edge to the other. Its central region, the dense bulge of ancient stars surrounding the galactic core, rises to a thickness of roughly 1,000 light-years. It contains somewhere between 100 billion and 400 billion stars. NASA and ESA place the estimate in that range, because counting individual stars across 100,000 light-years of gas, dust, and overlapping light is genuinely one of the harder problems in observational astronomy. The uncertainty alone, a 300 billion star margin of error, tells you something about the scale of what we are dealing with. Our sun sits approximately 26,000 light-years from the galactic center. It occupies a position in a relatively minor spiral feature called the Orion Arm, sometimes called the Orion Spur, a smaller structural offshoot wedged between 2 of the Milky Way's more prominent spiral arms. the Sagittarius arm on the side, closer to the center, and the Perseus arm on the side, facing outward. We do not live on a main artery of the galaxy. We live on a quiet lane between them, in a neighborhood that the galactic map treats as a footnote. At the center of everything, at the gravitational anchor around which the entire galaxy slowly wheels, sits Sagittarius A star. This is a supermassive black hole with a mass of approximately 4 million times that of our Sun, compressed into a region smaller than our solar system. For decades, it was known only through its gravitational influence on the stars orbiting furiously around it, some of them completing full orbits in just a few years at speeds of millions of miles per hour. Then, in 2022, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a glowing ring of superheated gas encircling a core of absolute darkness. One of the most extraordinary photographs in the history of science. It sits 26,000 light-years from where you are sitting right now. At the speed of light, reaching it would take 26,000 years. The center of our own galaxy, the place that everything here orbits. The gravitational heart of our entire stellar home is 26,000 years away at the maximum speed the universe permits, and crossing the full width of the galaxy from one side to the other would take 100,000 years at light speed, the fastest motion that will ever exist. Here is a detail that makes this feel less like a number and more like a lived reality. Our Sun is not sitting still inside this structure. It orbits the galactic center at approximately 230 kilometers per second, completing one full lap in somewhere between 225 million and 250 million years. Astronomers call this span a galactic year. Since the Sun formed roughly 4.6 billion years ago, it has completed approximately 20 of these galactic orbits, 20 laps around the center of the Milky Way, across the entire lifespan of our star. In those 20 galactic years, everything that has ever lived on Earth came and went. The first single-celled organisms appeared, survived for billions of years, and eventually gave rise to complex life. Forests rose and collapsed. Dinosaurs dominated the planet for over 150 million years and vanished. The entire span of human existence, from our earliest ancestors to every civilization ever built, fits inside a fraction of a single galactic orbit, so small it barely registers on the scale. 20 laps. The full history of life on Earth, and we have not crossed 1% of the galaxy's diameter. The planets within that galaxy are staggering in number. Data from NASA's Kepler Space Telescope mission established that on average, every star in the Milky Way hosts at least one planet. Apply that ratio across even the conservative estimate of 100 billion stars, and you get 100 billion planets in our galaxy alone. Estimates for the number sitting within habitable zones close enough to their stars for liquid water, far enough to avoid being scorched, run into the tens of billions of potentially habitable worlds, spread across 100,000 light-years, each one a destination that has never been visited, never been seen up close, never been understood. If you traveled at the speed of light and spent just 1 second at each of those worlds before moving on, the tour would consume thousands of billions of years. The universe will not last that long, not even close. But the Milky Way, immense as it is nothing more than a single grain of dust inside a larger structure. And that larger structure, it is pulling us towards something we could not even see clearly for decades. What happens when you are being pulled toward a destination you cannot reach, even if the universe grants you infinite time? That is not a riddle. It is a description of something happening to you right now, at this very moment, as you sit reading these words. You cannot feel it. There is no sensation, no wind, no sense of acceleration. But every galaxy in our local region of the cosmos, including the Milky Way, including the Andromeda Galaxy, including every smaller galaxy bound together with them in what astronomers call the local group, is being drawn through space toward a single gravitational point at approximately 600 kilometers per second, not 600 kilometers per hour. 600 kilometers per every single second. That is more than 2 million kilometers per hour, sustained, continuous, and completely invisible to every human sense we possess. The destination pulling everything in this direction is called the Great Attractor. It sits approximately 250 million light-years away, in the direction of the constellations Centaurus and Norma. For decades, its existence was known only through inference, through the unmistakable signature it left in the motions of thousands of galaxies, all streaming in the same direction, drawn by something massive enough to redirect the flow of matter across hundreds of millions of light-years. Yet astronomers could not see it directly. The reason was frustratingly simple. The Great Attractor lies almost exactly behind the dense plane of the Milky Way itself, buried behind a curtain of dust, gas, and stars so thick that visible light cannot penetrate it. Scientists called this obscured region the zone of avoidance, not because anything dangerous lurked there, but because the Milky Way's own body blocked our line of sight so completely that studying what lay beyond was nearly impossible for most of the 20th century. It was only through radio telescopes and infrared observations, instruments capable of seeing through the galactic plane rather than being stopped by it, that the picture began to clarify. And what modern research has revealed is that the Great Attractor is not, by itself, the full story. It is a local concentration of mass real, substantial, and gravitationally significant. But it is itself being pulled towards something even larger. That something is the Shapley concentration, a colossal supercluster of galaxies sitting approximately 650 million light-years from Earth, carrying a combined mass roughly 10,000 times greater than the Milky Way. The Great Attractor is, in a sense, a waypoint, a ripple in a current that flows towards something larger still. Now hold the scale of this in your mind for a moment. 250 million light-years to the Great Attractor. At the speed of light, the fastest motion the universe allows reaching it would take 250 million years. That is longer than the entire Mesozoic era, the age that encompasses the full rise and fall of the dinosaurs, from their earliest ancestors to the asteroid impact that ended them. That entire sweep of Earth's biological history would not be enough time to cross the distance to the thing currently pulling our galaxy through space. And here is the cruelty built into this picture. We are falling toward the Great Attractor at 600 kilometers per second. But the expansion of the universe is simultaneously pushing the Great Attractor away from us. The space between us and it is stretching faster than our motion through space can compensate. We are in pursuit of a destination that is receding faster than we are approaching. Even a beam of light aimed directly at the Great Attractor today is running on a track where the finish line shifts outward with every passing moment. We are not getting closer, in the deepest practical sense. The Great Attractor is unreachable, not because of our technological limitations, but because the geometry of an expanding universe does not permit the gap to close. We are chasing something we will never catch, and we have no choice in the matter. In 2014, astronomer Brent Tully and his colleagues published a landmark paper in the journal Nature that reframed how we understand our cosmic address by mapping the flow of thousands of galaxies, tracking which direction they were all drifting, following the currents of motion like reading the flow of water across a landscape. They identified a single, connected superstructure of which the Milky Way, the local group, and the Great Attractor region are all a part. They named it Laniakea, drawn from Hawaiian words meaning immeasurable heaven. Laniakea stretches approximately 520 million light-years across. It contains roughly 100,000 galaxies. Its total mass is estimated at the equivalent of 100 million billion times the mass of our Sun, and we sit at its outer edge, not at the center, not in some prominent position, but at the periphery of one of the largest structures humanity has ever mapped. We have known this for just over 10 years, a structure 520 million light-years wide, and we only drew its borders a decade ago. There is something philosophically staggering about that. We are passengers in a current we did not choose, moving toward a center we cannot reach, inside a structure we barely had the tools to see. On a timeline measured in hundreds of millions of years, the cosmos does not ask for our consent. It simply carries us. If the Great Attractor and Laniakea have already unsettled your sense of scale, wait until I tell you about what lies between the superclusters. Not stars, not gas, not anything at all, and that nothingness accounts for the majority of the universe's volume. If you were placed at the exact center of one of the universe's great empty regions, what would the night sky look like? Take a moment to actually picture it. You are floating in space, oriented in no particular direction, with an unobstructed view of the cosmos in every direction simultaneously. Back on Earth, even on the darkest night far from any city, you can see the Milky Way arching overhead, a dense river of light stretching from horizon to horizon. Proof that you are embedded inside a galaxy teeming with hundreds of billions of stars. You can spot the smudge of Andromeda with the naked eye. You can identify constellations, planets, clusters. The sky, however dark it feels, is never truly empty. Now, remove all of that. Every single point of light, the Milky Way gone, Andromeda gone, every individual star visible to the naked eye gone, the sky above you in every direction would be an almost perfect, unbroken black. The nearest galaxy might be tens of millions of light years away in any direction you chose to look. You would have no frame of reference, no landmarks, no indication that the universe contained anything at all. A civilization evolving on a planet inside such a region might spend millions of years looking outward and conclude, with every instrument at their disposal, that their galaxy was utterly alone in an infinite void. They would be profoundly wrong, but they would have no way of knowing it. This is not a thought experiment set in some hypothetical corner of the cosmos. These regions are real, mapped, and far more common than most people ever consider. When astronomers pull back far enough to see the universe at its largest scales, what they find does not look like a sea of stars or a uniform scattering of galaxies across space. It looks like foam or a vast sponge. Galaxies do not distribute themselves evenly. They cluster into filaments, enormous rope-like structures stretching for hundreds of millions of light years, and into flat sheets and dense nodes where filaments intersect. And surrounding all of these structures, filling the spaces between every thread and wall of the cosmic web, are the voids, giant, nearly empty bubbles of space where almost nothing exists at all. The most famous of these is the Boötes Void, discovered in 1981. It spans approximately 330 million light-years in diameter. To cross it at the speed of light would take 330 million years. Inside a region that size, basic probability and the average distribution of galaxies across the universe would suggest the presence of thousands of galaxies. The Boötes Void contains fewer than 60, a space 330 million light-years wide, and it is almost completely empty. Astronomers who first measured it reportedly found the result so improbable that they assumed they had made an error. They had not. But here is something that lands closer to home. In 2013, a team of astronomers identified a structure they called the KBC Void, named after researchers Keenan, Barger, and Cowie. This is a region of significantly below average matter density, centered approximately on our own location in the universe. Its estimated diameter is roughly 2 billion light-years, making it one of the largest known underdense regions ever identified. The matter density in our immediate cosmic neighborhood is estimated to run approximately 20% below the universal average. We are not on the outside of a void looking in. We appear to be living inside one, drifting through a bubble of relative emptiness that dwarfs anything in our observable vicinity. The existence of these voids points towards something fundamental about the composition of the universe itself. Everything we can see, every star, every galaxy, every cloud of gas, every planet, every atom of ordinary matter in existence, accounts for approximately 5% of the total energy and matter content of the universe. According to data published by the Planck collaboration in 2018, 27% is dark matter, a form of mass that interacts gravitationally but emits no light and has never been directly detected. The remaining 68% is dark energy, the mysterious property of space itself that is driving the universe's accelerating expansion, what we call the visible universe. The entire luminous structure of stars and galaxies that fills our telescopes and our imaginations is a thin, glowing fraction of a much larger reality that we cannot see, cannot touch, and cannot yet fully explain. The cosmic web itself, that vast network of filaments and walls within which all visible matter is threaded, has been modeled in extraordinary detail by the illustrious TNG project, one of the most comprehensive cosmological simulations ever run, using supercomputers to simulate the gravitational and hydrodynamic interactions of matter across billions of light years. The illustrious TNG team produced models of large-scale structure that match real observational data with remarkable precision. The web is real, the voids are real, and the voids dominate. If you measured the total volume of the observable universe and asked what fraction of it contains galaxies, stars, and ordinary matter in any meaningful density, the answer would be a small minority. The overwhelming majority of the universe's volume is void empty, dark, and silent on scales that make our entire galaxy look like a dust speck pressed against a window pane. The universe is not an ocean of stars with empty spaces between them. It is an ocean of emptiness with the thinnest imaginable web of light stretched across it, and we have spent most of human history staring at that web, mistaking it for the whole picture. These voids are not simply nothing. Some physicists argue they may hold the answer to the greatest mystery in the universe, the force that is making it expand faster and faster, with no sign of stopping. If something invisible is continuously taking away everything you can see, and it makes up 68% of everything that exists, what would you call it? Sit with that for a moment. Not as a rhetorical flourish, but as a genuine accounting of reality. More than 2/3 of everything in the universe is composed of something that emits no light, occupies no detectable position, registers on no instrument ever built, and yet is the single most consequential force shaping the ultimate fate of the cosmos. It is not hiding in some distant corner of space. It is here, in this room, in the space between your hands right now, and it is winning quietly, invisibly, and without any possibility of being stopped. The discovery that this force existed came in 1998, and it came as a shock to nearly everyone in physics. Two independent research teams had set out to measure something they thought they already roughly understood: the rate at which the universe's expansion was slowing down. Since the Big Bang, space had been expanding outward. Gravity pulling all matter toward all other matter was expected to be gradually applying the brakes. The question the teams were trying to answer was simply how much the brakes were working. To measure this, both groups studied a specific category of stellar explosion called Type 1a supernovae. These events are extraordinarily useful to astronomers because they always release the same intrinsic amount of energy, which means their apparent brightness in the sky directly reveals how far away they are. By mapping the brightness of these supernovae at various distances, the teams could reconstruct the history of the universe's expansion with precision. What they found shattered the expectation entirely. The distant supernovae were dimmer than they should have been, which meant they were farther away than any slowing expansion could account for. The universe was not decelerating, it was accelerating. Space was expanding faster now than it was billions of years ago, and the rate was increasing. Saul Perlmutter, Brian Schmidt, and Adam Rees led the two teams to this discovery and were awarded the Nobel Prize in Physics in 2011. The force driving this acceleration was given the name dark energy. That name, however, represents the full boundary of our certainty. We do not know what dark energy is. No detector has ever registered it directly. No experiment has isolated it in a laboratory. We know only two things about it: It constitutes approximately 68% of the total energy content of the universe, and it is pushing everything apart at an ever-increasing rate. Dark energy does not cluster. It does not concentrate around galaxies or drain away into voids. It is a property woven uniformly into the fabric of space itself, present everywhere, at all times, in equal measure. And here is what makes it so consequential. As the universe expands and new space is created, the total amount of dark energy grows proportionally with it. More space means more dark energy, which drives faster expansion, which creates more space, which produces more dark energy still. It is a cycle with no natural break, no upper limit, and no end in sight. Now bring that directly to the question of what it means to travel at the speed of light. Because dark energy does not merely make the universe large. It makes large portions of it permanently, irrevocably unreachable, and it is actively making that situation worse with every second that passes. When a beam of light leaves Earth heading toward a distant galaxy, it must cross the space between here and there. But that space is simultaneously expanding. For galaxies close enough to us, our light outpaces the expansion and eventually arrives beyond a certain distance. However, the accumulated stretching of space along the full length of the journey adds up faster than light can compensate. The galaxy effectively recedes faster than the light can close the gap. That critical boundary, the distance beyond which nothing sent from Earth can ever arrive, is called the cosmic event horizon, and it currently sits at approximately 16 to 18 billion light-years from us. Everything beyond that line is gone, not distant in a practical sense, not waiting for better technology, gone in the deepest physical meaning of the word, permanently beyond the reach of any ship, any signal, any photon that will ever leave this planet. The numbers that follow from this are staggering. The observable universe contains approximately 2 trillion galaxies. Of those 2 trillion, only the fraction sitting within roughly 16 to 18 billion light-years from us could in principle ever be reached at the speed of light. That fraction amounts to less than 3% of all galaxies we can currently observe. More than 97% of the visible universe galaxies we can photograph, measure, and study in detail already lies beyond any possible journey. We can see them. We will never touch them. The light arriving from them is the last contact we will ever have, and the horizon is not holding steady. Dark energy is shrinking it. Galaxies sitting just inside the reachable boundary today will, as the expansion accelerates further, eventually cross that line and vanish from our reach permanently. This is not a distant threat measured in trillions of years. It is happening now, continuously, with each passing second carrying some portion of the universe beyond the point of no return. In approximately 150 billion years, virtually every galaxy outside our own local group will have crossed the horizon entirely. Their light, already in transit toward us, will be stretched so severely by the expansion of space that it will never complete the journey. Those galaxies will still exist, burning, evolving, aging, but they will be beyond any knowledge we could ever acquire. To observers living in our region of the cosmos at that future time, the sky will appear nearly empty. The 2 trillion galaxies filling our current sky will have vanished without a trace, carried off by expansion into a silence so complete that no evidence of their existence will remain detectable. This is what makes our present moment extraordinary in a way that deserves genuine recognition. We exist during a narrow window in cosmic history when the universe is still fully visible, when 2 trillion galaxies still send their ancient light across space, and that light still reaches us, still carries information about the structure of everything that exists. Any civilization arising in our region of the cosmos, more than 100 billion years from now, will inherit a sky that has been stripped bare. They will look outward with the finest instruments they can conceive and conclude that their galaxy floats alone in an infinite void. They will be completely wrong, and they will have absolutely no way of knowing it. The evidence will simply be gone, erased by the same invisible force that fills 68% of the universe right now. We are here during the window. That is not a minor thing. That is perhaps the most remarkable accident of timing in the entire history of intelligence. But before everything disappears, there is one galaxy that is not retreating. It is not being carried away by dark energy. It is coming toward us. No light-speed ship required, no propulsion system needed. It is arriving on its own, drawn by gravity, on a course set billions of years ago. And the collision it will bring will be the largest cosmic event this region of space has ever witnessed, if Earth is still here to witness it. When two galaxies collide, what do you think actually happens to the stars inside them? Most people, when they hear the word collision applied to galaxies, picture something catastrophic, a violent smashing of stars into stars, a cosmic demolition derby played out across millions of light years. The kind of destruction that leaves nothing recognizable behind. The instinct makes sense. We live in a world where collisions mean damage, wreckage, impact. A car striking another car, a wave breaking against a cliff. The assumption carries naturally upward in scale. Two galaxies, each containing hundreds of billions of stars, meeting head-on, surely the result would be the most violent event imaginable. The reality is stranger, quieter, and in its own way more beautiful than any explosion could be. Andromeda, catalogued by astronomers as Messier 31, is the largest spiral galaxy in our local group. It sits approximately 2,537,000 light-years from Earth. And on a clear moonless night far from city lights, you can see it with the naked eye as a faint smudge of light in the constellation that shares its name. When you look at it, you're looking at roughly 1 trillion stars, 2 to 3 times the stellar population of the Milky Way, all bound together by gravity into a disk of light that has been traveling toward your eye for more than 2.5 million years. And it is not staying where it is. In 2012, astronomers using data from the Hubble Space Telescope confirmed what earlier observations had long suggested: Andromeda is approaching us. Not drifting vaguely in our direction, moving toward the Milky Way at approximately 110 kilometers per second, drawn by the mutual gravitational attraction between the two largest members of our local group. The calculations that followed from those measurements were precise enough to project a timeline. The first close encounter between the two galaxies is expected approximately 4.5 billion years from now. Full merger, the point at which the two galaxies have gravitationally entangled themselves into a single structure, is projected at roughly 6 to 7 billion years from now. These are not estimates hedged with uncertainty about whether the collision will happen. It will happen. The only remaining question is the precise geometry of the encounter, and even that has been narrowed considerably by ongoing observations. Now back to that original question. When the two galaxies meet, what happens to the stars? Almost certainly nothing dramatic, at least not in the way the word collision implies. The reason comes down to the same principle that has appeared throughout this story: the overwhelming emptiness between stars. The average distance between neighboring stars in a galaxy is measured in light years, trillions of kilometers of empty space separating each sun from the next. When two galaxies pass through each other, that vast spacing means the probability of any two individual stars actually striking each other is extraordinarily close to zero. Astronomers have studied dozens of galaxy mergers across the universe through telescope observations, and direct stellar collisions appear to be essentially non-existent events. The galaxies interpenetrate like two clouds of smoke, merging each star threading silently through the spaces between the stars of the other galaxy. Gravitationally nudged, but physically untouched. What does happen, and what makes galaxy mergers spectacular to observe from a distance, is gravitational sculpting on an enormous scale. As the two galaxies pull at each other during their first pass, tidal forces distort both structures dramatically. Long streamers of stars' tidal tails, stretching across millions of light years, are flung outward into intergalactic space. The graceful spiral arms of both galaxies are torn apart and reshaped. Stars that spent billions of years in stable, predictable orbits find themselves redirected onto entirely new paths. Our own sun could be displaced significantly from its current position in the Orion Spur, flung outward or inward by the gravitational turbulence of the encounter over hundreds of millions of years. Gravity draws the two distorted structures back together. They pass through each other a second time, and eventually the orbital energy dissipates enough that the combined mass settles into a new configuration. What emerges from this process is not a spiral galaxy. Spiral structure depends on the organized rotation of a relatively undisturbed disk of gas and stars. The violence of a merger, even one as gentle as galaxy mergers, tend to be disrupts that organization irreversibly. The result is an elliptical galaxy, a smooth, rounded, slowly rotating mass of stars with no arms, no disk, and relatively little of the cold gas needed to form new stars. Astronomers have already given this future galaxy a name. Some call it Milkomeda, others prefer Milkdromeda. Either way, it will be a quieter, more diffuse structure than either of its parents. By the time Milkomeda takes its final shape, our sun will be approximately 10 to 11 billion years old. Stars of the sun's mass and type do not last forever. As hydrogen fuel in the core runs low, the sun will expand dramatically, swelling into a red giant, large enough to potentially engulf the inner planets, including Earth. The oceans will have long since boiled away. The surface of our world will have been sterilized. Whatever remains of humanity at that point, if anything does, will have had billions of years to find somewhere else to go. The merger with Andromeda and the death of the sun are not separate crises arriving simultaneously. The sun's expansion will likely render Earth uninhabitable before the galaxies complete their full merger, giving any surviving descendants of humanity an astronomically long warning window to act on. The night sky in those final billions of years of Earth's habitability will be unlike anything we can currently see. Andromeda, now a faint oval smudge, will have grown across the heavens into an enormous glowing structure, its light rivaling the Milky Way overhead. The two galaxies slowly weaving together in a gravitational dance that no individual human lifetime could witness in full. The collision with Andromeda is coming, and nothing will stop it. But there is something even more certain arriving for every corner of the universe, and it brings no collision, no explosion, no drama of any kind, only a cold silence spreading outward across trillions upon trillions of years. How would you feel knowing that the universe will not end in fire or collision or any dramatic final event, but in perfect cold, perfect stillness, and a silence so complete that nothing will ever disturb it again? That is not a poetic description. It is a straightforward projection of where the laws of physics are taking everything that exists, played out across timescales so vast that the numbers involved stop carrying any intuitive meaning at all. We live right now in what cosmologists call the stelliferous era, from the Latin for star-bearing. It is the age we have always known, the age our entire existence has unfolded within. Across the universe, stars are being born inside collapsing clouds of gas and dust. Galaxies blaze with light. New suns ignite. Planetary systems assemble. The cosmos hums with energy, flowing from one form to another, from nuclear fusion in stellar cores, outward through space as radiation, warming whatever surfaces it encounters across light years of empty dark. This era began shortly after the Big Bang and will continue for approximately 100 trillion years from now. 100 trillion years. The current age of the universe is 13.8 billion years. The stelliferous era has barely begun, but it will end. Star formation is already slowing across the cosmos. The reservoir of cold gas from which new stars condense is finite, and galaxies are consuming it. Eventually, the last stellar nurseries will exhaust their supply. The last new star will ignite, burn through its fuel over millions or billions of years, depending on its mass, and go dark. No replacement will follow. The stelliferous era will close not with any singular event, but with the quiet extinguishing of the final sun in the final galaxy. What follows is the degenerate era. The universe will still contain objects white dwarfs, the dense burned-out cores of stars like our sun, cooling slowly over unimaginable timescales. Neutron stars, the collapsed remnants of more massive stars, spinning silently through the dark. Black holes, the gravitational monuments left behind by the most massive stellar deaths. But no new light sources, no fusion, no warmth generated anywhere. Just the slow cooling of embers in an expanding, darkening universe stretching across timescales that dwarf the entire stelliferous era by factors that language struggles to contain. Beyond that lies the black hole era, beginning around 10 to the power of 40 years from now, a number so large that writing it out as 10 followed by 40 zeros still fails to communicate its magnitude. By this point, even white dwarfs and neutron stars have faded or been disrupted. Only black holes remain as significant concentrations of mass. And even black holes are not permanent. In 1974, Stephen Hawking demonstrated theoretically that black holes slowly radiate energy, a quantum mechanical process now called Hawking radiation, over extraordinarily long timescales. This radiation causes black holes to lose mass and eventually evaporate entirely. The most massive black holes in existence will take the longest, but none are exempt. One by one, across spans of time measured in numbers with dozens of zeros, they will dissolve. And then comes what cosmologists call the dark era. Beginning around 10 to the power of 100 years from now, there are no stars, no black holes, no significant energy gradients anywhere. The fundamental particles that remain may themselves eventually decay through processes that operate on these extraordinary timescales. Temperature approaches absolute zero asymptotically, never quite reaching it, but draining away toward a stillness so complete that no physical process of any consequence occurs anywhere in the universe, ever again. Entropy, the measure of disorder, of energy spread so uniformly that no useful work can be extracted from it, reaches its maximum possible value. The universe arrives at perfect equilibrium, and in perfect equilibrium, nothing happens, not slowly, not occasionally, nothing, permanently, for the remainder of time. This outcome is demanded by the second law of thermodynamics, one of the most ironclad principles in all of science. Entropy in a closed system always increases or remains constant. It never decreases spontaneously. The universe is the ultimate closed system. Every star that burns, every collision that occurs, every thought that forms inside a biological brain increases the total entropy of the cosmos by some infinitesimal amount. We are all, in our own small ways, nudging the universe toward its final silence. The direction is fixed. The destination is certain. Now, hold the number 10 to the power of 100 alongside the current age of the universe, 13.8 billion years. The comparison is not like comparing a year to a century, or a human lifetime to the age of the Earth. The gulf between 13.8 billion and 10 to the power of 100 is so extreme that no analogy drawn from human experience can bridge it honestly. The entire current age of the universe, set against 10 to the power of 100 years, is less than a single frame in a film of incomprehensible length. Everything that has ever happened, every star, every planet, every ocean, every civilization, every thought ever recorded, has occurred in what amounts to the opening instant of the universe's total lifespan. Our existence in that frame is not even a footnote. It is something smaller than a footnote in a document so long that no intelligence that will ever exist could read it in full. But from precisely that vanishing fraction of cosmic time from this impossibly brief window, a question rises that cannot be quieted. If the universe is this vast, this lonely, and ultimately destined for perfect cold silence, why are we here, asking about it? If there are hundreds of billions of planets in the Milky Way alone, what is the actual probability that we are the only ones asking questions about any of this? That is not a comfortable question to sit with. It has no clean answer, no settled resolution, no consensus among the scientists who have spent careers thinking about it. But the tension it creates between the mathematical near certainty that life should exist elsewhere and the complete, unbroken silence that greets every attempt to find it is one of the most genuinely unsettling puzzles in all of science, and it connects directly to everything we have been discussing tonight, because the same distances that prevent us from traveling to other stars also prevent us from knowing whether anyone is out there at all. In 1961, astronomer Frank Drake sat down with a small group of colleagues and wrote an equation, not an equation designed to be solved, more of a framework for organizing ignorance. The Drake equation lays out the chain of factors that would determine how many communicating civilizations exist in the Milky Way right now, the rate at which stars form, the fraction of those stars with planets, the fraction of those planets with conditions suitable for life, the fraction where life actually emerges, the fraction where intelligence develops, the fraction where technology capable of detectable communication arises, and finally the average lifespan of such a civilization before it goes silent. Multiply all those fractions together, and you get an estimate. The problem, and the reason the equation remains both famous and unresolved 60 years later, is that almost every variable in it carries enormous uncertainty. Plug in optimistic values, and the galaxy should be teeming with civilizations, perhaps millions of them. Plug in pessimistic values, and the answer collapses to one, meaning us, alone in the Milky Way, by chance, or by the particular difficulty of the path that led to us. And then there is the question that Enrico Fermi reportedly asked in 1950, casually, over lunch, in a way that turned out to carry more weight than anyone at the table expected. If intelligent civilizations are common in the galaxy, where is everyone? The Milky Way is roughly 10 billion years old, even at speeds far below light speed. A civilization with a modest head start could have spread probes, signals, or colonies across the entire galaxy many times over in that span. The fact that we have found no trace of any such expansion, no signals, no megastructures, no unmistakable technological signatures anywhere in the sky demands an explanation. This tension between expectation and observation is what we now call the Fermi paradox. Several explanations have been proposed, and none of them are entirely comfortable. In 1998, economist Robin Hanson introduced what he called the Great Filter, the idea that somewhere along the path from simple chemistry to spacefaring civilization, there exists a barrier so extraordinarily difficult to cross that almost nothing makes it through. The unsettling question is where that filter sits. If it lies behind us, if the emergence of complex life, or of eukaryotic cells, or of multicellular organisms, represents the nearly impossible step, then we may be among the rare few who made it through, and the silence around us is the sound of a galaxy full of chemistry that never quite became biology. If the great filter lies ahead of us, however, if it is something that advanced civilizations reliably encounter and fail to survive, then our apparent solitude is not reassurance, it is a warning. A second explanation is the rare Earth hypothesis, which holds that the specific conditions that allowed complex life to emerge on Earth, a large stabilizing moon, a Jupiter-sized planet deflecting incoming asteroids, the right distance from the galactic center, the right stellar type, plate tectonics, a magnetic field of sufficient strength, are so improbable in combination that planets like ours are vanishingly rare. Perhaps unique, life may be common in simple microbial forms, but the conditions required for intelligence may occur almost nowhere else. A third possibility, drawn from what has been called the dark forest model, proposes that the silence is not absence, but strategy. Any civilization sufficiently advanced to broadcast its existence across the galaxy is also sophisticated enough to understand that revealing your location to unknown others carries existential risk. In a universe where the distances between civilizations preclude meaningful diplomacy before conflict, the safest behavior may simply be to listen and never transmit. Under this model, the galaxy is full of civilizations holding their breath. And then, there is the explanation that connects most directly to the theme of tonight. Signals may have already arrived, They may have washed over Earth before humans existed, or before we had instruments capable of detecting them, or during the brief windows between our telescopes pointing in the right direction. The cosmos is old. The window during which two civilizations overlap in both time and technology may be extraordinarily narrow. One moment from the history of our own listening effort stands apart from all others. On August 15th, 1977, astronomer Jerry Emmon was reviewing data from the Big Ear radio telescope at Ohio State University when he noticed a signal so strong and so precisely structured that he circled it on the printout and wrote a single word in the margin: "Wow." The signal lasted 72 seconds, came from the direction of the constellation Sagittarius, and matched almost exactly the characteristics theorists had predicted an extraterrestrial transmission might have. It has never been detected again. It has never been explained. More recently, the James Webb Space Telescope detected the chemical signature of dimethyl sulfide in the atmosphere of the exoplanet K2-18b, a world approximately 120 light-years from Earth. On our planet, dimethyl sulfide is produced exclusively by living organisms, particularly marine phytoplankton. The detection, reported in 2023 and still under active investigation as of 2024 and 2025, has not been confirmed as biological in origin. Alternative non-biological chemical pathways are being rigorously examined, but the molecule is there, in the atmosphere of a distant world, waiting for an explanation. We may not be alone, but the distances that prevent us from traveling to other stars impose the same barrier on any conversation we might try to have with whatever else is out there. The galaxy may be full of voices, each one isolated by the same light speed limit that confines us, each one calling into a silence too vast for any answer to cross in a meaningful time. We may never truly meet. But if we cannot go, is there another way physicists have spent decades thinking about shortcuts through the fabric of space-time itself, and what they found is both breathtaking and brutal. If science tells you that something can exist, mathematically, does that mean you can actually build it? The honest answer is no. And the story of how physicists learned that lesson in the context of faster-than-light travel is one of the most instructive in modern science. It is the story of what happens when the equations of general relativity are pushed into territories their creator never intended. And what emerges from that exploration is simultaneously the most imaginative and the most humbling set of results that theoretical physics has ever produced. In 1994, Mexican physicist Miguel Alcubierre published a paper that immediately captured the imagination of anyone who had ever dreamed of crossing interstellar distances in a human lifetime, working within the mathematics of general relativity, the same framework that describes how mass curves space-time and how that curvature governs the motion of everything from planets to light. Alcubierre demonstrated that it was theoretically possible to construct a configuration of space-time geometry that would allow a vessel to travel between 2 points faster than light, without ever violating the rule that nothing moves through space faster than light. The mechanism was elegant. Instead of accelerating a ship through space, which would require infinite energy, as the ship approached the light speed ceiling, the Alcubierre drive would leave the space inside the ship essentially flat and undisturbed. The ship itself would not move through space at all. Instead, space in front of the vessel would be compressed, shortening the distance to the destination, while space behind it would be expanded, lengthening the distance from the origin. The vessel would ride this wave of warped geometry like a surfer carried by a swell, arriving at its destination faster than any light beam traveling through unwarped space, without ever locally exceeding the speed of light at any point. On paper, the idea is mathematically consistent. General relativity permits it, and that permission from the equations is exactly where the good news ends. To create the required geometry, the Alcubierre drive demands a form of matter with negative energy density, exotic matter that would need to exert a repulsive gravitational effect, pushing space apart rather than drawing it together. No such material has ever been observed in nature. The closest analog Is the Casimir effect a real, measured quantum phenomenon where two uncharged metal plates placed extremely close together experience a small attractive force caused by quantum vacuum fluctuations between them? This effect involves quantities of negative energy so minuscule that they are measured in fractions of a joule across microscopic distances. Alcubierre's original calculations required exotic matter with negative energy equivalent to the mass energy of Jupiter, the largest planet in our solar system, to create a warp bubble large enough to enclose a spacecraft. A 2021 paper by Harold White and Alexei Bobrik proposed modified geometries that reduced the exotic matter requirements significantly. But significantly in this context still means amounts of exotic matter with properties that have never been confirmed to exist in any quantity whatsoever in the natural universe. The reduction from Jupiter mass to something smaller does not help if the starting material is entirely hypothetical. The wormhole faces the same fundamental obstacle from a different direction. First described mathematically by Albert Einstein and Nathan Rosen in 1935 as a consequence of general relativity's equations, which is why they are sometimes called Einstein-Rosen bridges. Wormholes are theoretical tunnels connecting two separate points in space-time. In principle, a wormhole could link two locations billions of light-years apart, allowing passage between them in moments. The mathematics permits this. What the mathematics also shows is that any traversable wormhole, one large enough and stable enough for matter to pass through, would immediately collapse the instant anything attempted to cross it, unless held open by exotic matter with negative energy properties. The same exotic matter required for the Alcubierre drive. The same exotic matter that has never been observed. Even setting aside the exotic matter problem entirely and granting the wormhole's existence by assumption, a further difficulty emerges. A wormhole connects two specific points. To use it as a shortcut, its far end must already be positioned at your destination before you depart. There is no known mechanism for placing the exit of a wormhole at a point across the galaxy. You cannot aim it. You cannot extend it. You can only pass through it to wherever it already connects, which raises the question of how it got there in the first place. In 2013, physicists Juan Maldatzina and Leonard Susskind proposed a remarkable theoretical connection, now called ER equals EPR, suggesting a deep mathematical equivalence between wormholes and quantum entanglement. The phenomenon where two particles remain correlated regardless of the distance between them. This connection has generated significant theoretical interest and ongoing research, but it remains a theoretical framework at the frontier of physics, with no demonstrated pathway to practical application on the scale of interstellar travel. The honest summary is this: warp drives and wormholes are not technologies waiting to be engineered. They are mathematical structures that require forms of matter with properties never observed anywhere in nature, at energy scales that exceed the total energy output of human civilization. Multiplied by factors so large, they become meaningless. They sit not at the edge of what our engineering can reach, but at the edge of what the physical universe may permit at all, and possibly beyond it. So the shortcuts are closed. The universe will not be folded. If we cannot go there, can we at least see it? The answer to that question is yes. And the James Webb Space Telescope has just shown us things that no one genuinely believed we would ever be capable of seeing. When you look at a photograph of galaxies from 13 billion years ago, what exactly are you seeing? The past or the present? The instinctive answer is the past. But slow down on that for a moment, because it is not quite right. That photograph is not a memory retrieved from some cosmic archive. It is real light, physical light, striking a mirror this very second after spending 13 billion years crossing the universe to get there. So when you look at that image, you are not remembering anything. You are experiencing the present moment. It simply happens that the present moment, on this particular occasion, is made of ancient light. This is precisely what the James Webb Space Telescope was built to capture, and it has done so more completely than any instrument humanity has ever constructed. JWST launched on December 25, 2021, and began full scientific operations in July of 2022. The total cost of the mission reached approximately $10 billion. Its primary mirror spans 6.5 meters across 2.7 times the collecting area of Hubble. But the dimension that matters most is not size. It is wavelength. JWST observes primarily in the infrared. The reason for this choice lies in the nature of an expanding universe. Light from the most distant galaxies has been stretched by that expansion to such a degree that its wavelength has been pushed entirely out of the visible spectrum. It has not dimmed so much as it has shifted, moved into a register human eyes were never built to perceive. JWST exists specifically to listen for those silent, shifted wavelengths. What it found there reshaped the field. In 2024, astronomers confirmed JADA's GS-Z14-0, the most distant galaxy ever observed. It existed when the universe was only about 290 million years old. The light now arriving at JWST's mirror left that galaxy 13.5 billion years ago. Consider what that means. When that photon began its journey, there was no sun, no Earth, nothing resembling our solar system. It traveled through the birth and death of countless stars, through the slow assembly of the Milky Way itself, only to land precisely on a golden mirror parked at the second Lagrange point in the year 2024. That same year, a cluster of galaxies nicknamed the Cosmic Gems was identified, 6 extraordinarily bright galaxies from the universe's infancy, brighter and larger than theoretical models predicted they had any right to be. This discrepancy is not a failure of science. It is the opposite. It is a crack in the model wide enough for new understanding to enter a sign that something about how galaxies assembled in the early universe may need to be rethought. And then there is K2-18b. The planet mentioned earlier, the detection of dimethyl sulfide, a molecule that on Earth is produced exclusively by living organisms. Unconfirmed. Still under active investigation, but enough to hold the attention of the entire field. There is a philosophical weight to all of this that is easy to miss in the technical detail. Every image JWST captures is, quite literally, a time machine. We have sent nothing backward through time that remains impossible, but the past has been sending its light toward us all along, patiently, across billions of years, waiting for something with eyes to be standing in the right place when it finally arrives. Yet even JWST, for all its reach, runs into an absolute wall. It cannot see past the cosmic microwave background, the boundary marking roughly 380,000 years after the Big Bang. That boundary is the final wall of light. Beyond it, no free-traveling photon exists for any telescope, however advanced, to ever capture. JWST has carried us to within 13.5 billion years of the beginning. But there is something older still arriving at Earth, not ordinary light, but the residual echo of the very moment the universe came into being. And remarkably, we have already mapped that echo with a precision that borders on the unbelievable. If you could photograph the universe at the exact moment it turned 380,000 years old, what would that photograph look like? It sounds like science fiction. It is not. That photograph has already been taken, and in a very real sense, it is hanging around you right now, in every direction, at every moment. First, a correction worth making clearly. The Big Bang was not an explosion happening inside space. The way a bomb detonates inside a room, it was the expansion of space itself, beginning from a state of extreme density and extreme heat. According to data from the Planck satellite released in 2018, this occurred approximately 13.787 billion years ago. With an uncertainty of only about 20 million years, a staggering level of precision for an event that far in the past, for the first 380,000 years, the universe was a place where light could not travel freely. It was too dense, too hot, conditions resembling the interior of a star. Photons were trapped, constantly scattering off charged particles, never able to travel any meaningful distance before being absorbed or redirected again. Then something changed. The universe cooled enough for electrons to bind permanently with protons. In an event called recombination, neutral hydrogen atoms formed, and in that instant, the universe became transparent for the first time. Light was released free to travel in every direction, unobstructed, for the remainder of cosmic history. Here is the remarkable part, that light is still arriving. Right now. It has been stretched by the universe's expansion, cooling from an original temperature of roughly 3000 Kelvin down to just 2.725 Kelvin today, barely above absolute zero. This is the cosmic microwave background, the baby picture of the entire universe. The European Space Agency's Planck satellite, operating from 2009 to 2013, mapped this radiation with unprecedented detail. Its data confirmed the lambda CDM model, the standard model of cosmology, and pinned down the precise proportions of dark energy, dark matter, and ordinary matter discussed earlier. But the true wonder of the CMB is not that it is old. It is what hides inside it. Tiny temperature fluctuations, differing by only about 1 part in 100,000 across the sky, are the seeds of every structure that exists today, every galaxy, every supercluster, the entire cosmic web described earlier. All of it traces back to quantum ripples that occurred in the first fractions of a second after the Big Bang, later stretched across billions of years into the scaffolding of the visible universe. In other words, the structure of everything you have heard about tonight: the Milky Way, Andromeda, the Great Attractor, Laniakea, is the magnified shadow of microscopic noise recorded in a snapshot taken when the universe was 380,000 years old. But the CMB is also a wall. It is the absolute limit for any optical telescope. No matter how advanced its design, no free photon exists from before recombination, because before that point, as established, light simply could not move unobstructed. To look beyond that wall, scientists cannot use light at all. They must turn to an entirely different signal, gravitational waves, a frontier, where observatories like LIGO and LISA are now pioneering. We have read the universe's birth certificate, a letter written in light, dispatched 13.8 billion years ago, only decoded in the last few decades. But that letter raises a question with no answer yet. In hand, our universe might be only one among countless others. And if that is true, every distance discussed tonight is no more than a single grain of sand in an incomprehensibly larger desert. If there are countless other universes existing in parallel with our own, would that make your existence more meaningful or less? Sit with that question honestly for a moment, because there is no comfortable answer waiting on either side of it. But before going further, something needs to be said plainly, without the theatrics that usually surround this topic. The multiverse is not an established scientific fact. It is a prediction that emerges from certain physical theories that are themselves well supported in other respects. But the multiverse itself has never been observed, measured, or confirmed. Anyone presenting it otherwise is not being honest with you. What follows is presented in that spirit, fascinating, mathematically serious, and entirely unproven. The simplest version comes from physicist Max Tegmark, who calls it the Level 1 multiverse. Its logic requires no exotic new physics at all, only an old idea taken to its natural conclusion. If the universe is infinite, or even merely large enough, then every possible arrangement of matter permitted by the laws of physics must eventually occur somewhere, simply because there is enough space and enough particles to exhaust every combination. This is not mysticism. It is probability operating at an almost incomprehensible scale. And one consequence of that logic, if it holds, is unsettling somewhere within that vastness. A configuration of atoms identical to you, down to the last detail, would also exist. Not a metaphorical double, a physical one, arranged by the same blind statistical inevitability that arranges everything else. The next layer comes from cosmic inflation itself, the same theory used earlier in this story to explain the seeds embedded in the cosmic microwave background. Physicists Alan Guth and Andre Linde developed a version of this idea known as eternal inflation, in which the rapid expansion that birthed our universe never fully stopped everywhere. Instead, it continues in places beyond our observable horizon, perpetually spawning new bubble universes, each one breaking off with its own independent set of physical constants. In some of these bubbles, gravity might be slightly stronger. In others, the charge of the electron might differ just enough that atoms, and therefore chemistry, and therefore anything resembling life, could never form at all. Then, there is the version that emerges from string theory, by far the most mathematically extreme. String theory requires extra spatial dimensions beyond the three we experience, and those extra dimensions can be curled up into an enormous number of distinct geometric configurations. Each configuration would produce a universe with its own unique physical laws. The number of possible configurations is estimated at around 10 to the power of 500. Try to hold that number for a second. It is not simply large. It exceeds the number of atoms in the observable universe by a margin so extreme that comparison becomes meaningless. 10 to the 500 different possible universes, each with potentially different rules for how reality itself behaves. Here is where intellectual honesty has to take over from wonder. The overwhelming majority of these multiverse models share a single, crippling limitation: they cannot be tested. A universe beyond our cosmic horizon, by definition, can never send us a signal, never produce an observable effect, never be confirmed or denied by any experiment we could ever design. This has led a number of physicists to argue, quite seriously, that much of multiverse theory does not belong to physics in the traditional sense at all. It belongs closer to mathematical philosophy, internally consistent, occasionally beautiful, but operating outside the boundary that has always separated science from speculation, the requirement of falsifiability. There is one narrow exception worth mentioning, because it shows how seriously some cosmologists take the search for actual evidence. Certain unusually cold regions detected within the cosmic microwave background, sometimes called cold spots, have been proposed by a handful of researchers as possible bruises, faint traces left behind by a collision between our universe and another bubble universe in the earliest moments after inflation. This idea remains speculative and unconfirmed. Most cosmologists consider it far more likely that these cold spots are simply statistical variations, ordinary noise within an already noisy sky. But the fact that anyone is looking for evidence at all marks where this conversation begins to brush up against something testable, however faintly. Whatever the final verdict on the multiverse turns out to be, one thing remains true, regardless. This single universe, the only one we have any confirmed access to, already exceeds every meaningful definition of distance the human mind can comfortably hold. We have measured its galaxies, mapped its voids, tracked its expansion, and still found ourselves unable to reach almost any of it. If countless other universes truly exist beyond this one, then the story of distance you have been told tonight does not end here. It does not even slow down here. It simply continues into a darkness we may never have the tools to illuminate. And perhaps that is the most honest place to leave this, not with an answer, because there isn't one waiting to be handed over, but with a question larger now than it was at the beginning of tonight, and standing patiently, exactly where we left it, for whoever comes looking next. We began with an imagined spacecraft and an imagined dream. We crossed the solar system in an afternoon, brushed against the nearest stars across years rather than lifetimes, and discovered that even our own galaxy is a prison of light, one that takes 100,000 years simply to cross from one edge to the other. Here is the final truth this journey has left us with. The universe was never built for us to explore it with our bodies. The distances are too vast, the timescales are too long, and dark energy is, at this very moment, quietly taking away piece by piece, galaxy by galaxy, the very things we are still able to see. And yet, here we are, standing on a small planet, orbiting an unremarkable star, in an unremarkable corner of an ordinary galaxy. And somehow, we understand all of this anyway, not because we have been there, not because we ever could be, but because we thought our way there instead. We are still standing at the edge of what we know. 95% of the universe, dark matter. Dark energy remains complete darkness to us, in the most literal sense. But that darkness is not a wall closing us out. It is an invitation, still open, still waiting. So the next time you look up at the night sky, remember this: every point of light you see is a letter from the past, sent from a place you will never reach. And in the exact moment you understand that you have already touched the stars,